Welcome to EDU World Space.
So in our first situation, we'll look at the annihilation of protons and antiprotons. So we have a total of 2n particles, and they are converted to photons. So what we need to do is think about the momentum that the photons will have. Now, the particles that get annihilated, we'll just say they all each have a mass of m. And this mass gets converted to energy, and the energy will be carried by the photons. So we'll end up with a total energy of 2n times mc squared. And this is going to be released as radiation, as photons. Now, a photon carries a momentum of p equal to E over c. E is the energy of the photon, and c is the speed of light. So if we have a total energy of 2n mc squared, then the total amount of momentum carried by all of the photons would then be 2n mc squared over c, which then is just equal to 2n mc. So that is the momentum that we can get from this process, where all of the particles are annihilated into photons. Now, in a second process, an alternative process, we have half of the particles get annihilated and the other half do not. So we have a particle that gives away, let's say that one of them gives away its rest energy. It gets annihilated and it gives away its rest energy, mc squared. So this particle is annihilated, and it gives away the rest energy to a particle of rest mass mc squared that is not annihilated. So this second particle, we have an energy relation for it. I'm going to go ahead and move down a little bit here. And we use the relativistic energy equation that relates the square of the energy to p squared c squared plus the square of the rest energy. So because the rest energy of the annihilated particle is added to the rest energy of this particle, the total energy becomes 2mc squared. So that is what you see right here. This is the total energy squared of the particle. It's the rest energy plus the energy given to it from the annihilated particle. This is whatever momentum, the square of whatever momentum this particle will now have. And this is the rest energy squared of the particle. So now we can get the momentum. We square the 2mc squared, we get 4m squared c to the fourth. That's all that this is. That's this term here. And we have p squared c squared. And we have, so this term is right here. And we have this term here. We're just squaring everything. So now we can subtract this term from this term here, and we get 3m squared c to the fourth equals p squared c squared, which means that the square of the momentum is equal to 3m squared c squared. We can take the square root, and we get the momentum of this particle is equal to the square root of 3 times mc. So if this happens, if this process is repeated n times, because we have n over 2 protons and n over 2 antiprotons, then the ejected particles can then have momentum of square root of 3 times n mc. That's how much momentum they could have. So that's actually the momentum the rocket will have, because that's what's transferred essentially to the rocket as far as momentum. So P will equal square root of 3 nmc for the rocket's momentum. So between these two processes, we see that the first process is more effective. because we get a higher speed for the rocket. 2 nmc is greater than the square root of 3 nmc. So this first process is more effective.